Yes, good afternoon. I'm Al Horn, and I've been in the R&D lab at Rogers Corporation for 25 years, and I'll be talking today about reducing active device temperature rise and RF heating effects with high thermal conductivity, low loss circuit laminates. So the summary here is in applications where heat must be removed through the dielectric substrate, substantial reductions in temperature rise can be achieved with high thermal conductivity circuit substrates, and in particular in cases where RF trace heating is significant, both high thermal conductivity and low dielectric loss contribute to substantially lowering the temperature rise. Now, when you're talking high thermal conductivity, everything is relative. Materials that are often cited are like chemical vapor deposited diamond and highly oriented planar graphite, but these are materials that are, of course, exotic, difficult to use, and often thermally conductive in one direction only. Metals are intrinsically very good thermal conductivity, but that's largely because the same thing, the properties that make things electrically conductive also make them thermally conductive. For insulator materials, the highest thermal conductivity dielectrics are ceramics. They're in the range of 30 to 170 watts per meter K. And when we get to organic composite circuit substrates, you'll see that there's an order of magnitude or two drop in what we're calling high thermal conductivity. But I guess what that makes, as I said, it's relative, because standard circuit laminate is often half an order of magnitude or an order of magnitude lower, and all of it is very high compared to still air. So now high-powered devices that generate a lot of heat need high thermal conductivity paths to the heat sink. That would be metals, if you can, or metal matrix composites if you need low CTE, or ceramics if you need a dielectric. And in many high-powered digital applications, heat is removed through the top of the device package by forced convection, and there's no way that organic substrates are going to be replacing those types of technology. However, in applications where the heat has to be removed through the dielectric itself, the fact that the high thermal conductivity polymer composites are significantly higher than normal circuit substrates can make them very, very useful to the engineer. And high thermal conductivity epoxy laminates have been used for more than 20 years in DC-DC power converters, solid-state relays, motor drive controllers, and LED circuits. But of course, these are low-frequency applications, so it's a high dissipation factor material, something like 0.025. But in recent years, there's been increasing interest in high thermal conductivity, low dielectric loss circuit substrates for high-frequency or high-speed digital applications. Most notably in high power circuits where RF trace heating can be significant, in applications where weight is a consideration, like remote radio heads where the power amp is attached to the antenna, smaller devices, and also high I/O digital devices. So what do you do to formulate a high thermal conductivity, low dielectric loss circuit laminate? You're unfortunately starting out at a disadvantage because the same properties that make for low dielectric loss also make for low thermal conductivity. And woven glass does little to increase the z-axis thermal conductivity, because it's a series arrangement, it's layered, so the insulator still acts like a good insulator. And the approach that's usually taken is to increase the thermal conductivity. You add as much low loss, high thermal conductivity ceramic powder as possible. So this is in a dispersed phase arrangement where you can often get a path or more of a parallel path between the two faces, and this helps increase the thermal conductivity. Candidate fillers for low loss laminates. Fused amorphous silica is widely used. It has a low dielectric constant, very low loss, a low coefficient of thermal expansion, and very good thermal coefficient of dielectric constant. And what kind of limits it for high thermal conductivity applications is it really isn't all that thermally conductive, about 1.4 watts per meter K. Aluminum is a fairly economical, very low loss material with a high thermal conductivity. However, it is a high dielectric constant and can be extremely abrasive. Aluminum nitride is another good candidate with very high thermal conductivity, but it also has a high dielectric constant, and these high decay values, will essentially limit the amount of the filler that can be added if you're trying to make a low dielectric constant laminate. Yeah, so our favorite is boron nitride, which has a high thermal conductivity of about 30 watts per meter K. It's soft, low loss, relatively low dielectric constant, and a very good temperature coefficient of dielectric constant. And we think it's the best choice for a low loss, low decay, drillable laminate material. So this is getting to the practical part of the study where we've tried to quantify the sorts of effects that you'll see in an actual circuit application. We've looked at FR4 with which is kind of a workhorse in lower frequency range, but with a high dissipation factor and a thermal conductivity around 0.4 watts per meter K. We've included two unfilled, low loss, high frequency materials. They're a hydrocarbon laminate and a modified PPO. Both of them are very low loss. They're about, again, 0.3 or 0.4 watts per meter K for thermal conductivity. RO4350B is a Rogers material that's highly filled with fused silica, the lower thermal conductivity filler, but that gets us to a considerably higher than the unfilled laminates at 0.7 watts per meter K. And then finally, a new material that we're introducing based on PTFE filled with boron nitride. There is a low dielectric constant, very low loss, and a 1.4 watt per meter K thermal conductivity. Yeah, so what we did to simulate, component heating was to use about a 6.2 millimeter square chip resistor. I think it's better just to jump to the diagram. The chip resistor was soldered to this pad into these lines, and we also had a version that had 8 thermal vias. So these are 30 mil holes with a mil of copper plated, to the ground plane. Yeah, we take, and again, I'll jump ahead to the drawing. We take those circuits with the chip resistor soldered on, glue it onto a 1/4 inch aluminum plate, which then gets bolted to a water-cooled heat sink. We paint we paint the circuit flat black, measure an emissivity in the oven with a forward-looking infrared camera, and then can generate thermal images. Yeah, and then what we do is go through, attach it up to a DC power supply, keep the thermal block at the right temperature, and then step through power levels and record the temperature rise. This is the prettiest part of doing any kind of thermal simulations. These are all on the same temperature range for colors. You can see that we're getting a 152 degrees C temperature rise on the modified PPO, about 135 on the FR4. The silica filler in the 4350 brings it down to 113, and the boron nitride filled brings it down an additional, substantial amount to about 100. The way to quantify this is to plot the temperature rise against the power dissipated in the resistor. You can see again for the PPO and FR4, you're looking at about a 20 degrees C rise per watt, with this substantially cut by about 30% with the 4350B laminate, and actually cut by 50% for the high thermal conductivity material. Yeah, this is with the thermal vias. You can see now we've gone from the range of 10 or 20 degrees C per watt down to 4 or 5 degrees C per watt. It narrows the differences between the materials because the copper in the vias, of course, at 400 watts per meter K is much larger than any of the dielectrics, but you can still realize an improvement in the temperature rise with a high thermal conductivity substrate. Yeah, for the RF trace heating experiments, what we did is put 50 ohm lines on 0.5 millimeter thick dielectric, and then again bonded it in the same system to our, to the water-cooled heat sink. Around the materials lab, we don't often have much of a source of high-power RF, but we did have a Sumatec Instruments passive intermodulation analyzer that we could put up to 30 watts out of at 1.9 gigahertz. So we did that and recorded temperature rise versus power level input. And you can see here that the FR4 is about 0.7 degrees C per input watt. A low loss material like the unfilled hydrocarbon or modified PPO, more than cuts that in half just by having a lower dielectric loss. The higher thermal conductivity of the 4350B can cut that further by about 30%. And compared to the FR4, you get a factor of 10 reduction with the low loss PTFE and boron nitride composite. Yeah, so this is just to summarize the Rogers laminates with enhanced thermal conductivity. I said the 4350B and 4003C, even though the silica filler is not the highest thermal conductivity material, it is substantially higher than most unfilled materials. Currently, what we have available is the RT Duroid 6035 with the 3.5 dielectric constant and 0012 loss. They're at 1.4 watts per meter K. And later on this year, we hope to be introducing 2 commercial versions of this material. There with a dielectric constant of 3.5, low loss, and a somewhat reduced by the presence of glass cloth thermal conductivity, and a dielectric constant 6 with a 1.7 or 1.8 watt per meter K. I said hopefully we'll be doing beta sampling later this year. Yeah, so that brings me to the conclusion that even though the thermal conductivity of these high high TC composite circuit substrates is low compared to other high TC materials, it can substantially reduce the temperature rise in designs where the heat has to be removed through the dielectric. Thermal vias substantially increase the effective TC of circuit substrates, but high TC dielectric composites can still improve thermal performance. And the combination of low loss and high TC can result in a substantial reduction in RF heating. And I thank you all for your time. Merci beaucoup.